is inside the ChemCo lab in Redwood City, California. That is pretty close to San Francisco. I'm Kreisler Lau. I'm the chemist who has been working on modifying and investigating the next generation epoxy asphalt formulations. Essentially, there are two types of epoxy asphalt formulations in use for the industry. The earlier version is type 5, and there were quite a few bridges that have already have the pavement installation on it, and they're working fine. These are all inside China, across the Yangtze River from Wuhan to Nanjing regions. John Bose and our retired field engineer, Dwayne Darno, were instrumental in helping the customers through the projects and bringing back the field results to help me along in the lab development. I have been mainly taking care of the chemistry side of the development of the formulations. Today we are actually more active in other areas, such as New Zealand, the Netherlands, the US FHWA, and Southern USA, with installations and tests and full-scale installations of diluted epoxy asphalt as binders for open-graded pavements. In New Zealand, epoxy modified materials now make up 25% of the New Zealand motorway systems. The newer version of epoxy asphalt formulation is called type 9, which has a higher polymer content with the expectation that it will give higher mechanical performance. And we need a mechanically stronger material for obvious reasons. Type 9 itself has further variants, namely the 1FLT and type 10. Epoxy asphalt is typically bonded with an epoxy cathode, namely type 1F, which is similar to the binders, but with higher tensile strength to offer. Now, my colleague, Dr. Ken Chen, will comment later in the real-world engineering applications of these materials, and also the composite testing procedures that he developed. At this point, I want to show you around the lab and give a little demo on how to handle the materials from the beginning to the very end, hopefully. So to start, I already have the epoxy asphalt Part B formulation in the oven to get softened, to be used later. And this has been at 125 degrees C for the past 45 minutes. And it depends on what type we're talking about. Some may require a longer heating time to get soft enough to handle. Can you dip the camera to kind of show this? Mm-hmm. This is a pretty good viscosity for pouring. So this is good. The hard part B, the calculated amount to be used later. Obviously, depending on which formulation we are playing with, the ratio of the two parts will change a little bit, but not by much. At this point, I am inserting the sample can into a jacket just to preserve the heat. And I'm fitting it into a typical stirring device. And setting it up to stir until this Part B material reaches a prescribed temperature, which is 250 degrees Fahrenheit or 121 Celsius. Shown over here, this is the stirrer that we typically use for stirring and during the mixing part of Part A going into the Part B. This is the thermocouple measuring the temperature. And depending on the material, the RPM would be anywhere from 500 to 700. That is the optimum range. Still from the camera, it is reading a little bit above 500. And this is going to take a little bit of time. So at this point, the temperature is around about the 250 degree F or 121 degrees Celsius. I'm going to be mixing Part A into Part B, which is being stirred right now in the stirrer. So the Part A has been in the oven to reach the temperature, and now it is. And I just pour it in. And the amount of Part A has been pre-measured, but then after pouring it in, I still have to remeasure the tear weight to make sure that everything is gone in. If not, I just use the heat gun to chase down the final several drops. And drop the reaction mixing can so that I could spin off the material off the stirrer. Okay, so this is how it look after mixing for about a minute or two. And qualitatively, it is actually a lot thinner because you're diluting the two things together. And at this point, I'm going to pour a small amount into this heated cuvette for the viscosity measurement. I'm setting up the viscometer to start the recording. Now the hot mode is being taken out from the oven, and I'm fixing it with a funnel. And after dispensing the viscometer sample. Now I'm pouring the remaining mixed liquid into the mold through the funnel. Now the filled mold will be returned to the oven for the curing time, which is 4 hours. Now at the end of the 4-hour cure time, I'm going to dislodge the casting from the mold. This is a hard casting after the mold has been opened. The next thing I wanted to do is to put some talc powder on it just to cut down the tackiness. After dusting off the talc powder, and this is how the casting looks like every time it comes out from the mold. And right now at this point, the only thing I need to do is to let it condition overnight and cut it into the testing specimens. So we come to the final part of the mechanical testing on this particular instrument with a small load cell. And after the casting came out from the mold, it will be cooled overnight just to let it condition. Then we use a die cutter to cut the dog bone test specimens. We're doing a demonstration on the instrument Tensile Test. The copper is in position and the tensiometer clips are on. And this is using a smaller load cell that we have for the purpose.
Hi, this is Ken speaking, and this is our aggregate and mixture lab. What I will show you is how to mix and prepare the epoxy asphalt mixture, and we are doing the Marshall samples, Marshall compaction, and I will start from here. The type 9 epoxy asphalt. That's 80.6 6. And with part A in the right ratio. And we put on the hot plate, turn on the timer, and we mix for about a minute and a half to 2 minutes by hand to make sure the part B and part A are mixed properly. Okay, oven, and we set the temperature at 280 Fahrenheit, which is about 140 C. Part A and part B into the hot aggregate. Okay, this is the aggregate fully mixed, and we put into the oven at 121 C, 250 Fahrenheit to cool for about 50 minutes. Then we bring it out and we'll compact it. Take the material out after 50 minutes and I will pour into the mold. "15 times around and 10 times in the center. And just use the spader to just mix it a little better. Then we set it up on the Marshall compactor, and this is the hammer. Six times each side. Okay, this is the compacted sample. I take out the paper. And go from both sides. We leave in the oven for another 4 hours, just like Ms. Lau did for the liquid epoxy asphalt. We do the same thing, like leave in the oven for another 4 hours to reach the full cure strength. After the mold the sample out of the mold and we measured its density, we will do the Marshall stability test. The Marshall stability test is running at 60 degrees C to simulate the material's performance under high temperature, around 60 C in the summertime. And this is the water bath at 60 C right now. We drop it in and we wait for 30 minutes, and then we will do the Marshall compression to measure its stability and flow them. No, wait a second, maybe I can. This is our instrument machine, and from here we do the compression and also tensile test. And later I will show you the Asphalt T245, which is the Marshall stability we made earlier. And besides that, we have the split head, indirect tensile split head for Asphalt T283. And from there we have some other this kind of testing head. This is for the interface shear test to test out the interface bonding strengths for our epoxy B1F epoxy asphalt. Okay, this is the sample out of water for 30 minutes. And this needs to be done in 30 seconds for Marshall stability test. Okay, after the test, the sample has been compressed and filled in this way. After the Marshall stability test and for the uncured sample and it's filled, as you can see this has been squeezed in this way, and the Marshall strength is about 3,000 pounds. 1/8 of an inch, so we put the other plate on top. We push it inside. Okay, from here. Yeah, I just want to show. What I'm trying to show you is how to make the composite beam fatigue sample, and this is the steel plate for 12 millimeter steel plate, and the steel plate is to simulate the isotropic bridge stacks steel plate for long span bridges, and as you can see, it has been sandblasted, and the next step would be to using the zinc paint, water probing, and corrosive resistant zinc paint to just spray paint on it. And after that, I will show you the mold. How does it look like? We'll put the steel plate into the mold. This is the setup of the mold to make the composite beam sample. Okay, this is the beam sample, and inside it we will spray the. We can use the spray gun to spray the B1F bond coat onto the steel plate, or we using just the brush to brush on it. And on top of that, we will prepare 4 kilograms of epoxy asphalt and lay down on top of the B1F bond coat, and we are going to from there we are going to compact it. After we connect the air hose to the air gun, then we can start to compact the sample, and we have using the square compaction head to compress the epoxy asphalt mix, and it is very noisy. It is very powerful. It needs to be really careful. And after the compaction is done, in the same way we move everything, which is about 40 pounds, into the oven for 4 hours curing, the same way we did for other epoxy asphalt samples. The final product will be like this. As you can see, the steel plate has been bonded very well with the epoxy asphalt concrete. The interface layer is the B1F bond coat we are using, and the overlay material is Type 9 epoxy asphalt mix. Type 9 epoxy asphalt binder. This is the 3-point bending fatigue test, and it gives a compression from 5 kilonewton all the way up to about 7 kilonewton until failure. It takes weeks to finish the test sometimes, and it gives a compression on the top flange and a tension at the bottom. So for this purpose, it's steel plates on top and the epoxy asphalt concrete at the bottom. So this test gives evaluate the tensile property of the epoxy asphalt overlay, and to simulate the real deflection caused by heavy load traffic on bridge deck. This is the dark form mode, and two papers put in there, one at the bottom, one the other on the top. We have the security here. Drop inside. Yeah. We use the spatula to kind of make it better looking. Put the other paper on top. Put it here. We move to the hydraulic compressor. down. These are the compression we did. Alright, that's about it. After compression, we put it back into the oven for 4 hours. Seems just like making cookies. This is final product coming out from the mold. B9. This is the setup of dark bone test for direct tensile. Conventional asphalt have a little to almost no tensile strength, but for epoxy asphalt, we have a very high tensile strength, and this is one of the ways we do the tensile test. The speed of it is 0.2 inch per minute until failure. This is our Instron E10000 electromagnetic fatigue testing machine. And this is our environmental chamber connected to the secondary AC. And for this test I'm running is the uni-axle fatigue test. I made the 2x4 column samples and glued with the top plate and the bottom plate, and running the direct tensile test. As you can see from the screen, it's at 10 Hertz per second, which means it's 10 times up and down per minute per second, and it gives 0.5 kilonewton load for tensile and minus 0.1 kilonewton load for compression in a 10 times per second cyclic load. The temperature inside this chamber is about 74 Fahrenheit at room temperature.